I want to record this. Do not feel like you need to show your camera, since I don't want you to feel like you're being observed or anything and no one else. People are going to be watching it, I hope, the recording. Okay, perfect. So growth models. First off, we have linear growth. Linear growth is like these two pictures, straight line growth. That straight line can also be horizontal, which would be zero growth, but that's an example of a linear growth. So linear growth has a constant increase or decrease. And in the wording in the homework, they will say things like every week or every month or every year or per year. So, for example, if you earn $17 for every hour you work, that's $17 an hour or $17 per hour. That is an example of a constant growth. Every hour you work, you get another $17. So if you follow your account, it's 17 and then 34 and then 51, etc. It keeps growing by 17 for every additional hour you work. So if you were to graph that 17, 34, 51, it would be a nice straight line pattern. The slope intercept tool from algebra, the y equals mx plus b, is the algebra model we use for lines. And we're going to look at a slightly different view of it, different letters and things for 1030, 1035, but it's the same basic model. The slope itself can be considered the increase or the constant rate of change. And the y-intercept is the initial value. So for example, on this one, we have a constant increase, positive slope or positive rate of change. And then if our line is sloping down, then we have a constant decrease, negative slope or rate of change. So an example of a constant decrease, if you're on the freeway driving home and every hour you are going 70 miles, so that's 70 miles per hour, then you can track that every hour the distance you have to go home will decrease by 70. Every hour, another 70 decrease, another 70 decrease. So it's constant. Now, if you're in the car and you speed up and slow down, then we now have to talk about the average rate of change. On average, were you going 70 miles an hour? Probably not. Maybe it's 62 because there's some slowdowns and hills and things, but maybe it is 70 or 71. Okay, so linear growth will be the easiest model we work with. We've already seen it in the prerequisite material, Math 990 perhaps you took, or Math, I believe we do that in Math 920 as well, the slope-intercept form. We'll also look at exponential growth. Now you can see from the graph, the exponential growth is much faster over time, although at the beginning, it's a slower growth. Imagine having a straight line right there. Actually, I can draw the straight line. Get all my tools ready. All right, tool. There we go. So if we had a straight line, oh, no, my tablet turned itself off. We're getting there. You can see at the beginning, a linear growth will be faster than an exponential growth. But over time, the exponential growth will catch up and then go much faster over time. Okay. So the things about the exponential growth is it's a relative increase or decrease. So it's often given as like a percent change. Your money is increasing at 4% per year. Or they can give you information about how long it takes to double or the half-life. Those are words that are usually used in an exponential growth or decay. You'll also often hear the word uninhibited growth law. And that just tells you that you're doing an exponential model. Now we notice this uninhibited growth. This growth just continues to skyrocket up. There's no limitation to how fast this goes. And we can see this some in society. Finances, there is no limit to how many zeros a computer can add to your bank account, depending on how much money you have. It just keeps growing. Population isn't really this, though, because we end up out of room or out of food. And so we originally thought this was how population grew. Thomas Malthus was the British mathematician that was studying the population in the United States as we marched westward in our ever expansion. Before we had, we were still buying land and everything else. Now, this is what he saw. He saw this exponential growth, uninhibited. Now, what really happens is the logistic growth. It goes exponential until you start running out of food, and then it tapers off and limits, and you end up with, a constant population. So, more about exponential. The graph is an exponential curve. You might or might not have seen that in your prerequisite material, but probably in high school sometime in the past you did. One side of the graph goes horizontal. In this case, we can see the left side is flatlining. Left side is going horizontal. I have compound interest, finances, bacterial growth, also until the bacteria use up all the food source, exponentially grows. We can also have the exponential decay. So this is often seen in radioactivity. This is when you would be dealing with half-life information. In this case, the right side is going horizontal. So one side is always going horizontal on the exponential growth models. You're either starting from almost nothing and increasing, or from a huge value, decreasing to almost nothing. And there are two others, but we don't use those much in this class. But in all cases, one side is going horizontal. All right, that leads us to the last model. It's called logistic growth. And it's a percent also. The percent growth rate is given, but along with that, you're given what's called the carrying capacity. I've heard teachers talk about this in terms of carrying with a K, or capacity with a K, because there's the K involved in the formula. And that can help you remember, oh, that's the capacity with the K, that formula. The carrying capacity really is, that's as much as that population can handle. Or in our case, that's as much as the earth can sustain. Or if you're in a pond looking at how many fish can be there, how many fish can live sustainably in that pond. That's called the carrying capacity. So the exponential growth, often they give you a percent increase or a percent rate, logistic as well, but then they also talk about this carrying capacity. That's the way that you know you're in a different type of model, the logistic growth model. So it is used in real-world populations. Primarily. There's other ways I've seen it used in how much oil is in oil reserves, etc. Okay, there is a complicated explicit formula. I'll talk about that in a bit. One of the hallmarks is both sides of the graph are going horizontal. So we're starting from very small growth, small population, and it increases exponentially, but then it starts to slow down the growth until it ends up going horizontal on the right when it's essentially approaching what's called the carrying capacity. So the spread of COVID, we saw this originally in China, the Wuhan. It was very, very, very few cases, and all of a sudden it burst out of China, and then eventually, and we were hoping for the herd immunity to kick in, enough people have it that it can't spread as easily. So if we were following one specific variant, this is what we would see. However, COVID is changing its variations, and so we get a new curve where there's hardly anyone with this new variant, and then it increases like crazy. And then it levels off as almost everyone has immunity or has had it, or is living in the mountains somewhere where no one can get to them. Rumors, the spread of rumors also happens. Hardly anyone knows it. Then that one person that tells everyone knows it, and all of a sudden it finally approaches, everyone knows it. And, that one last person that figures it out is like, why am I always the last one? Oh, someone has to be. The carrying capacity is the upper horizontal. This is also a picture of logistic growth. The right side is going horizontal, but it's taken a while to settle down to that carrying capacity. And the left side is going horizontal as well. This is the overshoot and collapse or correction behavior. If you have very fast growth, your population, for example, will shoot through the carrying capacity. You are now on borrowed time, essentially, and something happens and you die out until you're below the carrying capacity, and then you grow again. But your die off and your growth rates are so fast that there's no nice, slow, steady increase to the carrying capacity. Instead, it's this rapid growth, decay settling on. That just happens when you have a very fast growth rate. And again, the carrying capacity is this upper horizontal line. Are there any questions with the basic look of the shape of the different growth models we're going to work with? You can chat the question. You can speak up if you'd like. Dustin, you have your microphone off. Do you have any comments or questions?
Sorry, I had my headset muted. No, I was going to say I'm good.
Okay, excellent. Okay, so let's take a look at the explicit versus recursive models that we use. Well, first off, explicit means displayed or clear. So an explicit formula expresses the output in terms of the input, like we've seen with function notation and functions, and like y equals mx plus b. Slope-intercept is an example of an explicit formula. So to use an explicit model, you are usually given an input and asked for an output, but you could also be given an output and asked for an input. That's really it for once you have the model, how to use it. Recursive, on the other hand, means returning or repeating. So recursive formulas use previous values to find new values. This type of model is a step-by-step model. So you need to have a starting point, and you move forward from that point to the next point, step by step. So a real-world example of the difference between the explicit and the recursive models. If you have a treasure buried somewhere, an explicit model would be like having the GPS coordinate system. You look it up, you zoom right into the map, you know exactly where it's buried, you can go straight to it. You can just heli drop straight down to it. On the other hand, if you have a recursive model, that would be like a pirate's treasure map. It says start here, turn towards the highest palm to your left, hopefully the palm tree's still there, and then walk 50 paces, okay? Then turn to the right until the mountain's right on your left shoulder, and then walk 20, et cetera, et cetera. That type of one step at a time is a recursive model. And if you miss a step, you are not getting where you need to go. So it is really important not to skip any steps. You can't skip steps. You can't just like, oh, let's just jump over to where that X is. No, that's the explicit model. There is no X with the recursive model. Okay, so the explicit linear models. These formulas will be given on exams, the large ones. And so we just want to get used to using them. This is spoken P sub n. This is a subscript notation. P sub n equals P sub 0 plus dn. This is similar to our y equals mx plus b. N is usually in time, like how many months have passed, how many weeks have passed, how many years have passed, etc. It's basically the input, like the x was for slope-intercept form. P sub 0. Now, if n is time, then if time is 0, that's the initial value at time 0. Now, time 0 depends on what problem you're doing. So if we're talking about history, then time zero is the birth of Christ for 80% of the population on Earth. Some people have a different time zero. If you talk to a scientist, time zero is the Big Bang. And it just depends. If you talk to a political scientist that's talking about the deficit, then time equals zero is probably when the last president took over, because that's when the whole situation changed and they need a new model. So time equals zero. P sub zero is the initial output value. It is constant. It's like the slope intercept, the y-intercept. D is the constant change. It stands for difference. And it's the coefficient of n. It's like the slope. And P sub n is the output. It's like the y value. So let me zoom in a bit more so we can take a look at these. These are some examples that you might be given or you might be asked to come up with. These are all linear models. It's like the mx plus b form. So you want to get used to, for example, if you want to find P sub zero, that's the constant term. So in this case, 4 is the constant term. In this case, there is no constant term. The constant term is, in fact, 0. Here, the whole thing is the constant term. There's no n. That's all constant. So -7 is P sub 0. Then D, let's see, D is the coefficient of n. In this case, +2 or -3. There is no n. That's because its coefficient was 0. So, your turn. You can put it in the chat. What is P sub 0 and D for this next example? Oh, and it's the exact same one. I did not mean to do that. I'm going to make a note of that. I made these last night at midnight. I wanted to make sure that I had something for you. Reward people that show up. Anyway, the coefficient of n is 2. That's D. And the constant term is 4. You do the next one. What is P sub 0? Answer that one first. Put it in the chat. What is P sub 0? Now, there's only 2 of us in the class, so make sure you're both participating, if you would. That one is correct. And then what is D? So the coefficient of n includes the sign in front of it. So it's -2/7. And the sign is very important. If D is positive, this model would be an increasing line. If D is negative, the model would be a decreasing line. And of course, D is 0. This is a horizontal line, if we were to look at it. D also tells you that every step you increase 2. So often these models are I don't want to go there. I guess, okay, they're called discrete models. And so the n's are whole numbers or integers. So n equals 0 is the initial. So this could be, for an example, there are 4 stoplights in the small town. And every year, they've added 2 new stoplights. So initially, 4 stoplights. And the growth is 2, and it's constant. So 4 stoplights, then +2, 6, then 8, then 10, then 12, then 14. So this is actually, you can think of this as an add 2 pattern. It would be 4 and 6 and 8 and 10, etc. This next one, this is a subtract 3 pattern. So it'd be 0, and then -3, and then -6, and then -9, etc. This is a subtract 3 pattern. This is an add 0. It's just -7, -7, -7, -7, etc. This would be like your grandparents' password. They haven't changed it in a long time. Maybe not. So another add 2 pattern. This is why the sign is so important. This is a subtract 2/7 pattern. Okay, nice. The explicit exponential model. So again, this formula will be given. This time, there's the n in the exponent. Notice there's an n in the exponent. Pretty easy to spot when you're looking at it. Oh, there's an n in the exponent. Versus the linear, there's no exponents at all. Here we have an exponent, and it's the time variable, the independent variable, the input in the exponent. Okay, so n again is usually time. P sub 0 is still the input, the initial output, value, the initial value. R is the relative change. Now, R is often given as a decimal, but it always needs to be used in decimal form. So I should actually say always the decimal of a given percent rate. So the reason why I said it often they'll give you the percent rate growth, the growth rate, and you need to use a decimal form. And P sub n is the output. Okay. The examples. So every one of these has this n in the exponent. That's how you can tell it's an exponential model. The P sub 0, you could literally plug in 0 for n, and 1 plus 0.03 to the 0 is 1. That whole thing changes to 1. And -2 times 1 is -2. So you don't necessarily have to remember that the coefficient of this exponential term is P sub 0. You could just plug in 0. If you plug in 0 on this one, 1.27 to the 0 is 1, etc. Same thing up here. You could just plug in 0. If I plug in 0 here, I get 0. If I plug in 0 here, I get 4. So you could just plug in 0 to get P sub 0. That's what it means, the initial time at time 0. So that's the initial value. It's the coefficient of the exponential term. Pretty easy to spot. Sometimes you won't see 1. It's 1. Or you can just plug in 0. Anything to 0 is 1. Now the rate, the growth rate. In the formula, the base of the exponential is 1 plus r. So this one's written really nicely. 1 plus, well, that's clearly r. But this one, 1.27, isn't written as nicely. You can write it as 1 plus 0.27 if you'd like to get r. But you could also do a simple calculation where you just put the 1.27 in and subtract 1. Because the formula has a 1 in it, so if you remove the 1, you're looking at r. That makes it really nice for the ones that seem strange, like the 0.91. Subtract 1 from it. You're looking at r. So finish the r column. What are the two values for these last two examples for the growth rate r? What do you get? Okay, good. 0.15. Perfect. And what about the 0.4? Negative 0.6. Perfect. Negative 0.6. Now, if R is positive, we'll be dealing with an increasing exponential curve. And if R is negative, we'll be dealing with a decreasing exponential curve. Remember, the exponential curves, one side is going horizontal. The other side doesn't go vertical. It keeps growing in the other direction. In this case, left, in this case, right. Okay. So if R is positive, it's an increase. I could look at this problem and say this is a 3% increase problem. It's growing by 3%, growing by 27%. Now, if it's negative, it's decreasing by 9%, increasing by 15%, decreasing by 60%. Now, if you increase by 15%, then you'll be 115% after that increase. If you decrease by 60%, what's left over would be 40%. So there are ways to interpret these, but the skill involved is subtract 1 to get from the formula to the rate. And if you're given the rate, add 1 to get the number in the formula. So it's either subtract 1 or add 1 to go back and forth between the rate and what's in the base of the exponential in the formula. Now, what about p sub 0? What's p sub 0 on this first example for you to do? -5. And the second one? Yep, 6. Perfect. So this is the exponential growth model. Now the explicit growth model. Good news. I mean, I looked it up so I could put it in there. And it's a formula you could use if you needed to, but you don't need to in this class because we don't do the explicit model. We will do the recursive model, but the explicit model, I wanted to put it in there so you can see that we've actually saving you some trouble by skipping that. Well, one thing I do want to point out is K. K is the carrying capacity. So a way to remember this, capacity. And that'll bug you. You're like, oh, God, why did he do that? Oh, it's capacity with the K. If they tell you something about capacity, use the formula that includes the K. Not this formula, the recursive formula. There it is. Just so you can see, the recursive logistic model has the K in it. So if the problem talks about a carrying capacity, go to the formula with the K in it. Okay, so now we're into the recursive models. Now, with a treasure map, you have to be given a starting point. So they will almost always provide you with the initial value. I call it A, it doesn't matter, whatever it is, it's usually a number. As you can see in the examples, they'll give you an initial value. And then they'll tell you how to get to the next step. Now, this stuff, P sub n and P sub n minus 1, that looks really messy. It's like, what is going on here? I've never seen anything like that. But if you use the words previous value and next value, then this makes a lot of sense. To get the next value, take the previous value and add d. Adding d, that's a constant linear growth. And n is a whole number, 0, 1, 2, 3, 4. Initial value, same d. And again, P sub n minus 1, think of it as either the current, the one you're on, or the previous value. And P sub n, think of it as the next value. This one is just best to go straight into the examples. There we go. So P sub 0 equals 1. To get to the next one, take the current one and add 3. Well, if we start out at 1 and we add 3, 1 plus 3 is 4. 4 plus 3 is 7. This is just an add 3 sequence. 1, 4, 7, 10, 13, 16, 19, 22, 25. We can add 3 all day long. That's not very hard to generate the pattern here. What's important is that you learn to recognize that these are linear. They're linear because it's just an add 3. D is 3. Or a subtract 4. D is negative 4. Or a subtract 1. D is negative 1. This tells you it's an add 3 sequence. Or it's a subtract 4 sequence. Or it's a subtract 1 pattern. They give you the starting value, 32, for example, and it's a subtract 4. Just keep subtracting 4 over and over and over. Or they give you negative 4 starting value, and they give you D is negative 1. This is a subtract 1 sequence. So subtract 1, negative 4 minus 1, negative 5, minus 1, negative 6, negative 7, negative 8, negative 9, negative 10. And we're basically walking ourselves along a line going down. Negative 4, negative 5, negative 6, negative 7, negative 8, negative 9. And we're tracing out this negative linear pattern. So we have a few more here. First off, what is D for this next one? It's 2. Perfect. What's the initial value? 6. If this is an add 2 sequence, what's the next value? 8, and then 10, and then etc. Interesting thing about this, if you take a value in a linear model and subtract the previous value, subtraction is the difference. You'll find the difference is 2. 8 minus 6 is 2. This is why they call this D. D stands for the difference between a value and the value before it. That's where D comes from. Okay, next one up. 50. Oh, wait, this is the D column. D is negative 5. Initially 50. What are the next two values in here? Yep, 45, 40. Seems pretty straightforward. It is very strange looking, but it's not that hard to do. And that's really what I want you to come away from today's conversation is, yeah, this is growth models and these recursive definitions. It's like, looks weird, but they're not that hard to do. Okay, so what is D for this last example? Negative 0.1. Perfect. And we're starting off with 2.5. Many of you have a calculator with an answer button. I'm using a graphing calculator that looks very similar to the TI-30 brand of calculators, where the keystrokes are basically the same, answer buttons are basically the same spot. So if you were to put in the initial value, and then you take that value, which I'm going to call answer, and I subtract 0.1, go and hit enter, it will subtract 0.1. That's the next value, 2.4. If I hit enter again, what the calculator has done is store 2.4 in the answer button. So if I hit enter again, it'll bring up the previous instructions, which is answer minus 0.1, and it'll take this 2.4 and subtract 0.1. And every time I hit enter, it will work out another subtract 0.1 for me. So in this case, we can quickly generate these terms. I think this is one of the best ways to be able to do recursive definition using your answer button on the calculator. So 2.4, 2.3. So if we start off with -4, I'm redoing this example right here, and I just take answer -1 and hit enter a few times, there's the sequence. I think this will be worth your time practicing, assuming you have an answer button on your calculator. If not, you might think that this is worth it. So if I were to jump straight into stuff over here, let me just show you. And then into my chat window. There we go. So this third one, right, or yeah, this third one, p sub 0 equals -4. So you start with -4, -4, your initial value. Done. And then to code this in on the right side here, everywhere you see the p sub n minus 1, you use your answer button. Oh, I cannot do that with my mouse. So I have a pen. There we go. So that's -2 answer. -2 p sub n minus 1. Hit enter. 8. -16. 32, -64. There's the sequence. There's the pattern of numbers. Super easy. So this next one, p sub 0 is 3. So we start with 3. And then we code this in. Wherever you see the p sub n minus 1, put answer. So this would be 10. Answer. So we have 3 here. You can write it in if you'd like. And then there's the next two, 30 and 300. This is 3, and then 30, and then 300. Very easy to generate these terms in recursive definition. Even this bottom one, 2.5, 2.5, enter. You enter the initial value, p sub 0, and then the right side of the formula, you replace answer where it's p sub n minus 1. Look at this one. Constant sequence, which is an example of an exponential sequence, but it's a trivial exponential sequence. 2.5 and 2.5 and 2.5. Interesting. Now, to spot the R value, notice the R is the coefficient of this p sub n minus 1. So this is saying to find the next value, take the previous value and times 3. Another mistake found. 1. 1 times 3 is 3. 3 times 3 is 9. This is a times 3 sequence or pattern. That's all it is. It's a times 3 pattern. R is 3. This next one, you can think of it as a times 1/2 or a divide by 2, your choice. 32 times 1/2 is 16, times 1/2 is 8, or 32 divided by 2 is 16, divided by 2 is 8. But you can always think of them as times if you'd like. So times -2. -4 times -2 is 8, times -2 is -16, etc., etc. So the R is what it's timesing, times 10. This one is times 1/10. This one is the invisible times 1. It's the coefficient of this piece of n minus 1. So this is 50, and it's times 1/10, then it's 5, and 5 times 1/10 is 1/2, and etc., etc. All right. This formula for exponential will be given. You can see it's a times pattern instead of an add pattern. Add pattern is a constant rate, a constant increase. Times pattern is a constant percent change, like it's increasing by 5%. If you're given a percent, almost, unless it also says carrying capacity, you're dealing with exponential. Okay, so we have 13 minutes left. Let's take a stab at the recursive logistic model. This again will be given. It's a good thing because that looks nasty. We're given an initial value, and then it says the next value is found by taking the previous value and adding something to it. That something is the growth rate times 1 minus the previous value over the carrying capacity times the previous value. Just a recipe. It's an ugly looking recipe, but all it is just a recipe. So P sub 0 is still the initial value. R is still the growth rate. Often this will be given as, trying to think of the wording I've read, absent constraints, the growth rate would be like 6% or whatever. We talk about absent constraints. So if the pool was endless and the supply of clean water and food was endless, then the growth rate of these fish would be, but it's a carrying capacity problem. They still will give you the growth rate as if it had no constraints. That's R. K, capital K, carrying capacity with a K. That's the carrying capacity. P sub n minus 1 and P sub n, we know how to think through those. So in this example, I went color-coded because it's kind of crazy until you realize how easy it is with the calculator, how to actually do this. Again, it was too late when I made these. I'm so sorry. I'm going to have to change these. The initial value is 10, it's a given right there. The rate is 20%. Right here, R equals 0.2, which might have been given as a growth rate in percentage. But we always use the decimal in the formula. The carrying capacity is down here, is 300. Okay, so how will we use this? We have the P sub 0. We need the next one, P sub 1. So if I let n equal 1 in this formula right here, then I'll get P sub 1 equals P sub 0 plus 0.2 times. So all my P sub n minus 1s, when I let n equal 1, turn into P sub 0s. So if you look at this formula right here, this is where I have plugged in n equals 1 into the initial formula. I know P sub 0, so every one of these blue spots, I plug in the 10, and I get the green P sub 1. And I've rounded this. To find the next one, I plug that 11.933 into the previous spot location, the P sub n minus 1 location, and I work out P sub 2. And then if I plug that number in where the green blocks are now, then I'll get P sub 3. And if I plug that into where the green blocks are right now, I get P sub 4. One step at a time, I'm generating the terms in the logistic sequence. Now, let me demonstrate what this looks like on the calculator with the answer button. Starting with the initial value of 10, enter. I need to code this right side. Everywhere I see a P sub n minus 1, I'm going to use the answer button. So it starts off with answer button, and then plus and 0.2, and then there's a parenthesis, and then a 1 and a minus, and this is an answer button divided by 300. And then a right parenthesis, and then this is answer button. If I hit enter now, I've coded the formula where the answer button is currently 10, initial value, and I'll basically be working this piece out right there. It'll give me 11.933, and you'll see it actually gives me more information than just that. So I have a rounded answer here. That's no good. Here's the beauty of using the answer button like this for the recursive definitions. All I have to do is hit enter, and it'll plug this value into the previous formula, and that will be what we see in this yellow block. And if I hit enter again, then it'll plug in this value into the formula. And this is a very simple way that you can use the calculator to get you this recursive definition logistic growth. Now the carrying capacity was 300. I want to just do this for a bit. Oh, it's slowing down, it's slowing down, it's slowing down. Oh. We've almost filled up this poor pond. If you keep going, eventually it'll get close enough to 300 that the calculator can't see that it's different from 300, and it'll finally say 300. But actually, it never quite gets there. But you can see we are approaching the carrying capacity. Now, if I were to change the growth rate to be bigger, we might see this overshoot 300. Nope, not quite. Okay. Let me change the growth rate even bigger. So what I want to show is in our graphs, we're still doing this. It's nice and going up and approaching 300. If the growth rate is large enough, fast growth, we should see this. And that's what I'm seeing if we can get our calculator to do. So I'm going to change this growth rate to 1.9. This is now 190% growth rate. It just blew past the carrying capacity. And now it's going to die off. So we went too far, and now it's coming back. And now it's going to go too far, and it's going to come back, and too far, and come back. And eventually, this is going to level off to 300. This is what scientists are so afraid of right now with the global warming and the climate change, is the rate of carbon dioxide increase in our environment is fast. It's large. And we're worried about this kind of behavior happening with the climate. And sure enough, that's basically what's happening. The climate is very drastic. And this is what we were afraid of with approaching the carrying capacity of the carbon dioxide in the planet for the current climate that we had. And, you know, if we could have leveled it off a little bit, maybe we could have had this kind of climate change. Very slow, gradual. That would have been nice. I think it's too late. That doesn't mean that it won't eventually level off to a new normal. Maybe, I hope. So I kind of like this planet. Anyway, got a little political there, but this is what modeling is. You model in mathematics to kind of get you insights into reality. So hopefully you play around with your calculator with this answer button tool. It is so nice. It is so easy to use. And it'll help you when you get to the finance module as well. Knowing how to use the previous value. This keeps you from rounding. I do want to point out that had I done the same problem using 11.933 and using that in this value, it actually wouldn't have worked. It wouldn't give me the same answer. So if I go back, this will be my last hurrah, starting with 10. And I need to go back and change this to 0.2, like our original problem. There's 11.933. So now if I do 11.933 and plug that into the formula, so instead of letting the answer button be in the formula, I update the answer button, not with the long digits, but with just an approximation. Our answer is now wrong. It still rounds to the correct answer, but it's not what we got before. You do not want to round in the middle of your problem because that rounded error will compound and get worse and get worse and get worse. The more times you round, the worse your answers will be. And pretty soon you'll just be on a totally different growth plan and you won't match up with what you were originally trying to find. So if you use the answer button, then the calculator holds all of this 0.333333, all of it in to work in the next example, the next problem. And then you can write down the rounded answer, but then if you hit enter with your calculator, it uses all of the answer of which you wrote down the rounded answer of to get the next one. And that way you won't have errors. The answer button will be your friend. I hope you have one on your calculator. And I also hope that this was worth your time showing up today. I really appreciate that you were here and answering questions. I hope it helps. I think it's a lot better than trying to learn from the book only. You guys have any thoughts before we end?
I appreciate not only trying to grasp mathematic concepts, but also the impending doom of our planet in the same lesson. So I appreciate that.
The chaos, not the doom. It's just going to be chaotic.
I know you're still recording, but I had a question specific to your course.
Okay. So I'm going to stop the recording at this time. Somehow.
I don't know if my counterpart is also part of your 1035 online course. So
it might be 10:30 instead of 10:35. All right. Thank you so much.